So this is a practice test for chapter 4. The first problems, they're perfect radicals. You could either do these in your calculator or know them in your head. You don't need to do prime factor trees for a perfect radical. For part 1a, the square root of 121 is just 11. I have that memorized. Similarly, for 1b, I know what the fifth root of 32 is. If it's a perfect radical, you don't need to simplify with prime factor trees. That's just going to be 2. And for part C of number 1, the cube root of 27 is just 3. Anytime something simplifies to be a perfect radical, use your calculator, I'm fine. Question 2, you need to show some detail. So when I have a fraction exponent, I'm going to change the fraction exponent into a radical. There were 2 ways to reduce this, but the easier way is to do the radical first. So if I don't know the radical part of this, I'm going to do it on my calculator. It's a perfect radical. So the cube root part of this is going to be 4. And then I'm going to square it. The answer to 2a is going to be 16. I need to see some work. I need to see the problem written as a radical. I need to see the radical simplified. For part B, as a negative exponent, I'm going to make the negative exponent positive by creating a fraction with a 1 in the numerator. Then I'm going to change the fraction exponent into a radical. Then I'm going to do the cube root. The cube root of 64 is still 4. And then I'm going to do the exponent in the denominator of 4 to the 4th power, which is 256. So for 2b, if you just wrote down an answer that you punched on your calculator, I'm going to take most of the points off. I want to see the negative exponent made positive. I want to see the fraction exponent turned into a radical. I want to see the radical simplified before applying the exponent. Problem 3 is multiplying conjugates. I could get lazy, but I'm not going to. I'm going to do 4 multiplications here. I'm going to do 4 times 4. 4 times minus 2 rad 3, positive 2 rad 3 times 4, positive 2 square root of 3 times minus 2 square root of 3. First multiplication, 4 times 4 is 16. Second multiplication, positive times the negative is a negative. I multiply the 4 and the 2 and get 8 square root of 3. Third multiplication, positive times a positive is a positive. I multiply the 4 and the 2 and get an 8 square root of 3. Last multiplication, 2 times negative 2 is negative 4. 3 times 3 is 9. The last multiplication is minus 4 square root of 9. Since these were conjugates, the middle pairs are going to cancel. I'm left with 16 minus 4 square root of 9. The square root of 9 is 3. So I'm really left with 16 minus 12, and the whole answer to number 3 should just be 4. 4 are perfect square roots and perfect square roots and cube roots. I don't need to do prime factor trees if they're perfect. So in 4a, the square root of y to the 4th over the square root of 25. I can do both the numerator and the denominator with the prime factor tree, but I don't have to if there's not going to be a radical in my answer. And in the numerator, the square root has an implied index of 2 that's not written. I always can reduce by dividing the exponent by the index, and if that reduction doesn't give a fraction, that's the better way to reduce the letter rather than doing prime factor trees. The denominator, I know the square root of 25 is 5. So for 4a, this is just going to be y squared over 5. For 4b, I need to do the cube root of 64. That's a perfect cube root. I have it memorized. I could do it on my calculator if I didn't have it memorized. But because it's a perfect one, I don't need to do a prime factor tree. And for each of the letters, I could do prime factor trees, but the dividing the exponent by the index doesn't give a fraction. I don't have to do prime factor trees. So first, cube root of 64 is going to give me 4. And then if dividing the exponent by the index doesn't give a fraction, that's the quicker way to reduce. It gives the same result as reducing by prime factor trees, but prime factor trees usually we reserve when the reduction gives a fraction in the exponent. So for an answer for B, it's going to be 4x to the first and y squared. I don't need to write the exponent of 1 with the x, it's just assumed. Um, 5a wants me to make a table for the graph of f of x equals the cube root of x minus 2. It wants me to sketch a graph. It wants the domain and the range. And all cube roots that we graph, both the domain and the range are negative to positive infinity. So without even having a table, every cube root that we graph has the same domain and the same range. I'm just going to bank those. For my table in 5a, I'm going to take the radicand and set it equal to 0 and isolate the x. And in my table for 5a, I'm going to put 2 in the middle of my x column. I'm going to go smaller, and I'm going to go bigger. If you own a calculator that you can get the y's in one big computation, do them all at once, that's fine. I'll do the y's manually for 5a and using my calculator for 5b, but if you know how to get the table on your calculator, do the calculator. For this x, the first y is going to be f of 0 is the cube root of 0 minus 2. If I'm doing them manually, which is an inefficient way to do it, cube root of 0 minus 2, doesn't say round to 2 decimals, but we certainly had been. I'm going to round to 2 decimals and make this negative 1.26 for a y. And then f of 1 is going to be the cube root of 1 minus 2. This is the inefficient way to do my table, but it's fine. That y is going to be negative 1. F of 2 is going to be the cube root of 2 minus 2, which is going to be 0. F of 3 is going to be the cube root of 3 minus 2, which is going to be 1. And f of 4 is going to be the cube root of 4 minus 2, which is going to be 1.26 again. So now I'm going to graph those the best I can. I don't have a lot of room here, but I think I could fit it. So my x's need to go up to 4. And my y's just need to go between negative 2 and positive 2. I think that would be fine. And the best I can, I'm going to plot these as points. The first part of my table is x equal to 0, down 1.26, so maybe it's about there. And then x equal to 1, y equal to negative 1. X equal to 2, y equal to 0. X equal to 3, y equal to 1. X equal to 4, y equal to 1.26. And these cube root graphs all kind of have the same look. They kind of have a little squiggle to them like that. On my cube roots, I usually just make dots for each of the x points. I usually don't physically write any of the points in. When I do the square root, I usually label that first point that's not an error specifically because I need it for the domain and I need it for the range. So I'm going to do quick table on 4b. 4b, same structure, or 5b should I say. 5b gives me the function f of x equals the square root of x minus 2. It's supposed to make a table, sketch a graph, find the domain and the range. I don't know exactly the domain and the range, but every square root graph that we did, the domain was square bracket, comma, infinity, round bracket. The range was square bracket, comma, infinity, round bracket. So I'm going to bank on that being what my domain and my range look like. My table is going to be the same because to get my table started, I take the radicand, set it equal to 0, and isolate the x. So when I go to do my table, I'm going to put 2 in the middle of my x column. I'm going to go bigger and smaller. And now I'm going to lazily get my table. You can do the table like I did in part A, one step at a time. But on this calculator, if you've been doing tables with this calculator with me, we do mode and 7, square root, alpha in right parentheses for the x, minus by the equal sign and not negative, 2. I'm going to hit equals, and this is going to disappear. If I hit equals and it says g of x, just hit equals again. You haven't set your calculator up the best, but it'll be fine. But when I hit equals, I won't get g of x. If you get g of x, just hit equals. And start at 0, type in 0, then hit equals. End at 4, type in 4 and hit equals. And step 1, because my numbers and my x's are 1 apart, so type 1 and hit equals. And I need to write 2 columns. The first column says the first point is x equal to 0, y equal to error. And then the second point is x equal to 1, y equal to error. And then the third point is the big point, x equal to 2, y equal to 0. The fourth point, x equal to 3, y equal to 1. The fifth point, x equal to 4, rounded to 2 decimals, y equal to 1.41. So I'm only going to get to plot 3 points, but that's enough for me. On my x-axis, I need to get up to 4. And on my y, or f of x-axis, I really don't need any negatives because I'm not plotting any negatives. I probably just need to get up to 2. The first point I'm actually going to label. The first point that's not an error is going to help me get the domain in the range. The x will be for the domain, the y the range. So 2, 0, 3, 1, 4, 1.4. And these square root graphs all have the same look, kind of a half a view laid on its side. So that's my graph. The domain is going to start at the x coordinate of the starting point, which is 2. The range is going to start at the y coordinate of this point, which is the lowest point on the graph. Doesn't matter to me if you get, I actually prefer you to do this. Mostly I'm in mode 2, but I might be doing some prime factor trees. I'm going to go mode and then 1 until I get to the I problems, the square roots with negatives, and live in that right now because I might have to do a prime factor tree. So you can do your tables like this, or you can do your table slickly like I did. It doesn't matter to me. 6 wants me to change fraction exponents into radicals. It says write with radicals. Simple to do with 6. A of 6, I'm going to write the denominator of the fraction exponent is going to be the index, and everything else is going to be the radicand. So that 2x to the first is going to be the radicand. And anything to the first power is itself. I don't need a parentheses or an exponent when the exponent is 1. So this is the best radical notation for 6a. For 6b, the 2 is not in a parentheses. It doesn't go under the radical. It becomes a coefficient. The radical only applies to the x to the 1/4. The denominator of the fraction exponent becomes the index, and under the radical becomes the base and the exponent without the denominator. So because the 2 wasn't in a parentheses, it doesn't go under the radical. So the big difference between A and B is where that 2 is. In A, it's inside a parentheses, so the 2 belongs under the radical. In B, the 2 is not in a parentheses, so it goes in front of the radical. 7 wants me to write with fraction exponents. 6 says write with radicals. 7 says write with rational exponents, and rational is just a fancy word for fraction. So for part A of number 7, 3 times the square root of x, I need to think of that as square root with a 2, x with an exponent of 1, and I need to change the radical to a fraction exponent. And the 3, because it's not under the radical, doesn't get a fraction exponent. So the fraction exponent part of 7 is 3x to the 1/2 power. The nice way to do B is to think of this as the square root of 3 times the square root of x, which is going to be the second root of 3 to the first power times the second root of x to the first power. If I want to write this, I'm going to write both with the fraction exponents because both the 3 and the x are under the radical. The fraction exponent from the square root of 3 is 3 to the 1/2 power. The fraction exponent from the x square root is x to the 1/2 power. This is the answer that I would probably write. But if you worked ahead, it would actually be okay if you said this is 3x to the 1/2 power, because you could have thought of the problem like this. You could have thought of this as the second root of 3x to the first power, putting a parentheses in, grouping the 3 and the x together, and this would be what would reduce to 3x to the 1/2 power. They're both equal to each other. These are two equally correct answers for part B. I almost think the top one's a little easier to follow. Question 8 asks me to multiply the cube root of 2x times the cube root of 4x to the 5th. I'm going to multiply the numbers. 2 times 4 and get 8. I'm going to add the exponents on the letters. 1 plus 5 is 6. And now I'm going to figure out the cube root of 8 and the cube root of x to the 6th. I don't need prime factor trees if they're perfect. And the cube root of 8 is perfectly a 2. And for the x, I can divide the exponent of 6 by the index of 3, and it doesn't give me a fraction, which means I can reduce that without prime factor trees. I could have gotten 8 solved with prime factor trees, but they're slow, and if I don't need them, I'm not going to use them. For part B of number 8, which is the square root of 3x times the square root of 12x cubed, when you multiply two square roots, you get another square root. 3 times 12 is 36. I'm going to add the exponents on the x's and get x to the 4th. And then I'm going to simplify each piece separately, do the square root of 36 and the square root of x to the 4th. The square root of 36 I just know. I don't need a prime factor tree to make that into a 6. And for the x, because taking the exponent of 4, dividing it by the index that's not normally written but assumed, because that doesn't give a fraction, that's the better way to reduce. And the best answer for 8b is 6x squared. I could have got that using prime factor trees. It's just inefficient to do prime factor trees when the numbers are perfect radicals and the exponents divide and don't give you a fraction. Number 9, not so lucky, because 72 is not a perfect square root, and x and y have odd exponents, and doing the dividing the exponents wouldn't help me because I'd get fractions. Let me do a prime factor tree for 72 to reduce it. 72 is 2 times 36. 36 is 6 times 6. 6 is 2 times 3 and 2 times 3. The prime factoring is 2 times 2 times 2 times 3 times 3. If I'm in mode 1 on this calculator, I just would have went 72 equals shift in quotes. Tells me I get 3 3s and 3 2s and 2 3s. So for my prime factoring, I get a 2 and 3 in front of the radical and a 2 under the radical. So a 2 and a 3 in front from the pair of 2's and the pair of 3's, and a 2 under from the single 2 that I didn't box. The x is going to stay under the radical. I'm not going to divide, because if I divided the exponent of 1 by 2, I get a fraction. That's not good. There's only one x, it stays under. The y to the 7th, similarly, I'm not going to divide the exponent because I'd have to do 7 divided by 2, which is a fraction, and I don't want to have fractions. I'm forming groups of 2. From my 7 y's, I get 3 groups of 2 to get 3 y's out in front of my radical from each of those pairs, and 1 y under my radical for my single. I'm going to multiply these things outside the radicals together. 2 times 3 is 6. The y's multiply out to be y cubed. And I get a 2xy under my radical. 10 is doing the square root of a negative. The square root of any negative number is equal to the square root of the positive of that number times I. I don't know the square root of 98. It's not a perfect square root, so I'm going to do a prime factor tree for 98. Lazy prime factor tree, because I like them. 98 is 2 times 7 times 7. It's a square root, so anytime I get two of a kind, I get one of those out front. The single stays under, so the square root of 98 has a 7 in front of the radical and a 2 under the radical. That's the best answer, but I could have written this as 7i square root of 2, and it equally would be correct. I'm going to pause and do a part 2 because the video is going to hiccup here in a second.